Hello everyone, welcome to the video. Today we're going to talk about how we can relax the simulation box before we start doing any production run for MD simulations. So as we know, the first step of running any MD simulation is that we have to build a geometry or topology files for our MD simulations. So it's kind of very important that we set ourselves up for success by providing a reasonable initial structure and relax the geometry properly. So if we don't do that, the consequence will be that our simulation will become unstable, or it takes a long time to relax, or our simulation will simply not start at all. So it's very important that we get this right. So here is an example of a bad initial structure. So let's say we want to put two molecules in a box, this one and there's another one here, and you can see that I did it on purpose. Basically the two molecules are very close to each other and there are some overlap. So if I try to hit the run button, you can see I get this arrow. Basically this tells me that the initial structure is very bad and we lost the atoms. Today we are going to go over 3 different techniques that we can use to relax the initial structure for our MD simulations. And the underlying simulation engine that we're going to use is going to be LAMMPS, but I'm pretty sure other software also offers similar capabilities. So let's get started. So the first method that we're going to talk about is gradient descent. It's pretty straightforward. If you ever taken calculus class, you will get the idea immediately. So basically, we know the formula for calculating total potential energy, which is basically the summation of Lennard-Jones potential for non-bounded atoms. And we also have bond energy, angle energy, and dihedral, and sometimes improper. So this is going to be the total potential energy. So from there we can just basically calculating the force, which is going to be the negative gradient of the total potential energy. And then from there we can do different styles of minimization. For example, the most straightforward one is going to be steepest descent. So basically we have the force, and then we are just going to follow the downhill direction corresponding to the force vector. So another option is conjugate gradient, which I think is the default option for LAMMPS, which is more complicated than the steepest descent, but it converges faster. So if you are more interested in this, you can read out more about it on LAMMPS documentation page. So let's just do a quick demo. So here you can see we have 2 different molecules, and let me just change the position of some atoms to make it more interesting. And let me just make the configuration far away from equilibrium position, and then we can see how energy minimization will sort of bring the energy back to its equilibrium configuration. And let me just quickly run the energy minimization. I'm going to click relax, and you can see this is energy minimization that we're going to run. We can look at the LAMMPS script. So it's just the LAMMPS command that you're going to use if you want to minimize the energy. So let me just click it, and boom, you can see that the energy minimization works, and the positions of the atom sort of go back to its equilibrium position. So it's kind of cool. So the second method that I'm going to talk about is called NVE-limit. So let me just write it down. So just based on the name, you can see that it's very similar to running MD simulations under NVE ensemble. Basically, we keep the total energy of the system to be constant. The only difference is that we kept we kept how far an atom can move in a single time step. So let's say we set the distance to be 0.1 angstrom. So what that means is that for each time step, the most an atom can move is going to be 0.1 angstrom. So now you can see why it's very useful, right? Because if you have a very bad geometry where atoms are like overlapping all over the place, so if you calculate the total energy of the system, and you can see that the total energy is going to be huge, right? Because the distance between different pairs of atoms are very short, but because we kept how far an atom can move under NVE ensemble, over time the system will stabilize. So let me just give you a quick example. Let's say we have this polymer, right? And let me pack this polymer into the box. Let me maybe pack 15, or let's make it 20, and then we allow overlap. So you can see that this is a very bad initial structure because the atoms are overlapping all over the place. The red areas are places where atoms are overlapping. So let me just relax it under NVE-limit, and let's look at the command fix relax all NVE-limit, and 0.1 is how far an atom can move per time step, and let me just run it. So you can see from the blurred background, you can see that all the red area kind of disappeared. So let's wait a few moments. So you can see that now we have a sort of very clean configurations, and basically all the overlaps are now resolved, so which is good. We can try to run this under NVE ensemble to see if it's able to run. Yeah, so you can see that the system is running fine. The temperature is a little bit high. We can bring it down a little bit to 300. So you get the idea. So basically, NVE-limit is a very powerful tool to kind of relax the initial structure. So, but one thing that we need to mention is that so even though NVE-limit can kind of stabilize the system over time, but the force in the system should still be computable. So in other words, the position of two atoms in the system cannot be exactly the same, because that if r equals 0, we basically have a divide by 0 problem, right? No amount of NVE-limit can fix that. So this is something that we need to keep in mind. So as we demonstrated previously, NVE-limit is very, very powerful, and I would say it takes care of your simulation 95% of the time. But once in a while, you are going to encounter a situation like this. So here we have two molecules that are kind of stuck in a very weird position. So you can see they're kind of glued together, but they're actually two molecules. So I can highlight one of them, and we can run a simulation, and you would know what I mean. So you can see that even though we have two molecules here, but you can see that these two molecules are like kind of get stuck together, and there's really no way to escape this configuration, and this is clearly not a very physical state. So what's happening is that the system is kind of stuck in the local minimum, and so if we can take a look at the energy, you can see the energy is very high for a system that only contains two molecules. And let's try to use NVE-limit to try to relax the structure. You can see that it's not really working. The two molecules are still stuck together because the system is kind of stuck in the local minimum. So the third technique that I'm going to talk about is something called soft push. So basically what this method does is it replaces the normal non-bounded Lennard-Jones potential with a soft potential. So let me explain what I mean by that. So as we know, for Lennard-Jones potential, here is the definition. So we have V equals to 4 epsilon times sigma over r to the power of 12 minus sigma over r to the power of 6. So as you can see, so epsilon is the energy scale, sigma is the time scale, r is the distance between a pair of atoms. So you can see when r is very small, the energy is dominated by the first term because it's power of 12, which is, it's going to be a huge number when r is very small. So basically, when r is very small, the V is going to be huge. So the total energy, the system is just going to blow up. Basically, what soft push does is it replaces this equation with a soft potential. So let us jump to LAMMPS documentation and see the definition of this soft potential. So here you can see here's the formula for this soft potential. It has 3 parameters. A is a prefactor. We can change this number depending on different times, and R is the distance between atoms, and RC is the cutoff distance. So the first thing that I notice is that when R is 0, E is not infinity. So which means that even though when 2 atoms are overlapping, the total energy of the system doesn't really blow up, because so cosine 0 is going to be 1. So if we plug in 1, E is going to be equal to 2A. So it's a normal number, not a huge number. So that this is why it is called a soft potential, right? Because even when R is very small, the energy doesn't blow up. So here it also mentions that A is a prefactor that can be made to vary in time. So what we can do in practice is we can set A to be 0 when T is equal to 0. So that means even though when 2 atoms are overlapping, they literally cannot feel each other. So it's just going to be a very useful technique. Here, let's go back to our simulation page and see if we can use this soft potential to kind of help our molecules to unstuck. So now we are back to our simulation page, and let's try this soft push and see if it works. So I'm just gonna click relax, and I'm gonna click this unstick button. So you can see that these 2 molecules are separated now, and so they kind of get out of that unphysical state. And if we run dynamics, you can see that they are kind of attract to each other. And if we look at the energy of the system, it kind of looks normal. The total energy is not some crazy number, and so the temperature is around 300 K, which is what we set for our NVT simulations. So it works great. So now we can see that this third method really worked. So that brings to the end of the video. Thanks so much for watching. All the files that I used and created in this video are available to download using the link below. If you like to stay updated, please feel free to subscribe to my channel and blog. Links are below as well. I've also included my email address, so don't hesitate to reach out with any questions about the simulations or your research in general. I read every single email and I do my best to reply to all of them. See you in the next video.